You are looking at the distribution over a latent variable set. So you found posterior p of z given some data, but you don't have a closed form. It's quite complicated. How do you find the mode, the mean? How can you sample it? Maybe you can use a surrogate posterior, q, which is almost as good and is easy to work with. Welcome to this video. We will introduce variational inference. Welcome to this new video. Today we want to look at the variational inference and the evidence lower bound shorthand ELBO. For this we will first look at the problems that posterior induces and how we find a remedy with a surrogate posterior. Then we will derive the ELBO, and in the end we will look at some visual examples on what it means to use the ELBO in context of variational inference. In the intro, we've seen that we are working with posteriors over latent variable set. So here we have the posterior or the distribution over this latent variable set given some data that we observed. And even though I painted it here, in general, we don't have access to this closed form solution. And shortly we will see why. And the problem might not be as representative in one dimensions, but think of multiple latent variables and also a high dimensional observed space. So in general, we are looking at directed graphical models with observed variables, and I will call them x vector, and latent variables, which are z vector. And they can be of different size, they don't have to be equal size. So for instance, this can be an Rn vector and this can be an Rd vector. So let us note this down, they have different sizes. And of course, if we have access to the directed graphical model, we also have access to the joint distribution. So this is equivalent to saying we have the joint distribution, and the joint, recall, this was the probability over x and z. But now we observe the x, the x are the random variables that we can observe. So we observe them. So we observe x as a dataset D. So for instance, think of x being images, and latent variables that are related to these images could, for instance, be the camera angle, the lighting. And our task is now that we observe x as a dataset D, and we want to perform inference, which means that we want to use our knowledge on the data that we observed in order to find information on the latent variable. So we want to look at a couple of pictures and then we want to see maybe what kind of a camera angle they have in common. So the task is we want the posterior. And of course, we can always describe the posterior in terms of Bayes' rule, and then the posterior of our latent variable given under x, and we fix x to our observation d, is equivalent to the fraction of p of x given d under z times p of z over p of x being d. And recall, we have here the likelihood of our data or of our images, then we have a prior on our latent variables, and here we have a marginal. And the problem in defining this posterior or in finding the functional form of the posterior is in evaluating this marginal. So that's where the problem arises. The problem is the marginal. And in some other videos, you might have seen derivations where we worked in terms of the proportional, and then later on we found normalization constants. But this only works if we work in really simple functional forms where we can then identify normalization constants. And in general, that's not possible. And if we don't have a normalization constant, which is given by the marginal here, then we don't have a full probability density function over set. And the actual problem is we could express the marginal, but it's just encompassing operations that are intractable, because p of our random vector x is the integration over all latent random variables, so from z0 all the way to zd, over the joint of p of x and z, and then dz0 all the way to dz, capital D minus 1, of course, because we have d latent variables. And as said, the problem here is that this is an intractable. And intractable means incomputable, because think of really complicated models where you, for instance, want to describe images, and then you want to integrate over potentially 10, 100 dimensions. and you want to find closed form solutions for this. This is just impossible. So in general. Of course, there are exceptions, but here we are interested in real-world scenarios where this is not possible. So coming back to the task of making inference. Now that we've seen it's impossible to get this posterior, as again, even though I painted it down here, but this was just for visualization purposes of showing you that it is a complicated distribution. But what is our remedy? And the remedy is, as proposed here, to use a surrogate, because even though our output is complicated, it might only encompass certain features that could also be approximated by extremely simple distributions. And we've seen that our posterior is multimodal, it is not symmetric and so on, but it has this major peak here. And if we just fit a Gaussian to it, for instance, then we might be able to capture most of the posterior information, but still be able to handle it. So let's write down the remedy. And this means that instead find a Q of Z that is approximately P of Z under X observed with the data D. And we want to find this as good as possible. And here we also see where the second term in variational inference comes from, because that's a variational problem, and variational, that comes from variational calculus, because we want to optimize over functions. So optimize for a function. In conclusion, we are doing variational inference, so we optimize for a function in order to be able to perform inference. And as always in machine learning, in order to find something that is optimal, we need a loss metric. Or more generally, we need to evaluate how good the fit of these two distributions is, or how close this distribution is to the other. So I'll call this the goodness of the fit. And for this, we need to find a metric that is associated in some sort of the distance between the Q and the P. And that is, of course, the Kullback-Leibler divergence. And if you haven't seen the video on the Kullback-Leibler divergence, I would encourage you to go back and look at this beautiful concept of finding a distance between two distributions. So this is a distance between two distributions. And distance, of course, means that we have identical distributions if the scale divergence is 0. And the higher this value is, the further they are apart. And our task is now to minimize the KL. And of course, we are interested in surrogate posteriors, so we won't find situations where this KL is 0, but we still want to get those surrogate which is the best. So let's encode this in an optimization problem. So we find Q star of vector Z as the arc minimum over all Q of Z from a certain family of distributions. So for instance, think of Gaussians, over the KL divergence of Q of Z to P of Z under X given by the data D. And I will also use a shorthand notation for this one here. So I will say that is equal to P of Z given the data. And this means we have a random vector X and we observe it as data. It's just a convenient shorthand notation. And let me also note this down. That is a family of, let's also call it simple distributions. And of course, simple does not mean that we change the dimensionality. It just means that it has a simple or analytical functional form. Of course, we are still staying in the same dimensionality of our latent variable. And just to refresh the knowledge of the KL divergence, I just want to write it down once. So the KL of Q of Z and P of Z given D is the expectation over Z distributed according to Q of Z over the logarithm of Q of Z over P of Z given D. And then closing brackets for this one. And of course, if we have a continuous random variable, then we can express the expectation in terms of an integration. And then we get, well, the integration from Z0 to Z capital D minus 1 over Q of Z times the logarithm of Q of Z over P of Z given D, and then we integrate from Z0 all the way to Z capital D minus 1, and that's our KL divergence. And within this expression, we've seen it now multiple times. So we have the Q of Z, and the Q of Z is just something that we propose, but we also have the posterior in here. And recall the big problem was that we don't have access to the posterior, because if we had the posterior, then we could of course use the scale divergence in order to fit our surrogate. But we don't have the posterior. So actually we kind of created a new problem. Let us note this down. So, but we don't have the posterior. Also, let me put in a sad smiley, because it's kind of a nice idea, isn't it? But we can't do it because we don't have the posterior. And the only thing we have is the joint. So we only have the joint, and the joint is P of set and the data. Of course, this means that we have an X here, but of course I fixed it with the data. And we also don't have the marginal. So we are kind of like lost. But there is again a remedy, and the remedy is to rearrange. Of course, this sounds rather general, but trust me on this. We will reach a form where we can actually compute something. And that's what we want to reach, right? So for this, let us note down the KL of Q of Z and the posterior once again. And we have the integration over all sets. And I will use a shorthand notation that is mathematically not necessarily correct, but I will combine all the integrals into one and denote a vector set in order to integrate over set. Then we have our Q of Z times the logarithm of Q of Z over P of Z under the data, and then closing brackets for the logarithm, and then d vector set, which also mathematically I would say is not too correct, but it's just a shorthand notation in order to simplify it. And we just saw that we only have the joint distribution. We don't have the posterior, and we don't even have the marginal. But still, let us express the posterior in terms of the joint and the marginal. So we know back from Bayes' rule that we did up here that we could express the posterior as, well, the joint. That's just the joint in the numerator divided by the marginal, right? So we have that P of Z given D is, well, it's P of Z and D, of course the underscore for the vector, divided by P of D. And here this was the marginal. Then let's plug this into the expression here. And then we're getting, well, again, the integral over the Z vector. Then Q of Z times the logarithm of Q of Z times, well, then the marginal, because it's like inverted. So P of D divided by P of Z and D. Then dz, and closing brackets for the logarithm here. Well, okay, of course, now we reformulated our problem with another quantity that we don't have, but we can put this quantity that we don't have outside of the logarithm and create two separate integrals. And the first integral will read the integral over Z of Q of Z times the logarithm of Q of Z over P of Z and D, closing brackets for logarithm, dz, and then plus, so because we can apply the logarithms rule and the numerator, and then the product gets into the sum of these two quantities. And then we have the integral over Z of Q of Z times the logarithm of P of D, of the marginal, dz. And then we again see on the left, we have an expectation over this quantity. And here we also have an expectation over this quantity. So let us note this down. So here we have the expectation over Z distributed according to Q of Z over the logarithm of Q of Z over P of Z and D, closing brackets, and then closing brackets for the expectation, plus another expectation, again over the same distributions. And here we have then the logarithm of P of D. And then we see, we have a quantity that contains stuff that we know. So we know, or we have access to the functional form of the surrogate, and we have also access to the functional form of the joint, right? Because we have the directed graphical model. And here we have something that we don't have access to, but that's of course a constant quantity. We will look at it in detail in a second. Let us introduce another simplification or rearrangement, because the expectation over something that does not contain Z is just whatever the expectation was taken over. So we get here the logarithm of P of D, and here we have this quantity, but I will change the order in the logarithm, or in like I swap numerator and denominator, and then I have to put out a minus in order to make this like a valid change. So we have minus the expectation over Z proportional to Q of Z over the logarithm of P of Z and D divided by Q of Z, and then closing brackets logarithm and closing brackets expectation. Let me introduce a shorthand notation for this, and I will call it an capital L, or like this calligraphic L of Q, because it's a function dependent on Q, or a functional dependent on Q. And then we can write down our derivations in shorthand form. And recall, we did all this for the KL between the surrogate and the true posterior. So we have the KL is minus this L quantity of Q plus the logarithm of P of D. Well, of course, we call that P of D, well, that is the marginal. And the marginal, well, it's a probability, so it will be between 0 and 1. If we apply the logarithm to the marginal, we get something that is called the evidence. And it's called evidence because it's just the log probability of the data. And if we apply the logarithm to something that is in between 0 and 1, then we have a quantity that is negative. So this is something negative, or in other terms, it is smaller or equal to 0. Of course, we don't have access to it, but one thing we know for sure is that this quantity is fixed. And it is fixed because we observed this data set, and the probability of the data set does not change dependent on what kind of a surrogate posterior we choose, right? So it is a fixed quantity. So for instance, it is, let's say, minus 7.3 in whatever kind of scenario we're talking about. Then we can look at the KL divergence. We know the KL is a distance, so it has to be something positive. So let me also note down it is the distance between posterior and surrogate. Well, and if we have something positive here and something negative here, and in order to fulfill this equation, we need to also have something negative here, because negative is positive, and then it can cancel with the negative here and create something positive over here. So this has to be something negative. So it has to be smaller or equal to 0. And because in general we expect the KL divergence to be non-zero, because we choose surrogate posteriors that are not our true posteriors, otherwise we wouldn't have to solve a problem, right? So we expect this to be smaller than this one, because if it is smaller than this one, then it is negative, and then we kind of get our positive KL divergence. So it has to be smaller than log P of D. So it is smaller than log P of D. And we said that this is the evidence, and this one is smaller than the evidence. We call this the lower bound of the evidence, or in other words, the evidence lower bound, the ELBO. So it is the evidence lower bound, or in other words, the ELBO, which is just a shorthand notation for this. Let us note down the ELBO once again, because it is really important. So we have the ELBO, and the ELBO over Q is defined as the expectation over set over the set vector according to Q of set over the logarithm of the joint of P of set and D over Q of set, which was our surrogate. And that's a really important finding. And let me also note down the finding that we did here, that the evidence lower bound is always smaller than the evidence, but it can also be equal to the evidence. So L of Q is log of P of D if and only if the KL of our surrogate to the true posterior is 0, or in other words, if the surrogate is our posterior, right? So it will always be a lower bound. But I hope you get the message across, because let me go back to the original problem, which was that we want to minimize the KL divergence. And we said we can't compute the KL divergence because we don't have the posterior. But now we have something that is computable, and we know if it is 0, and we know if it is 0, then we have found the true posterior, which we won't in general, so we want to maximize it because it is a quantity smaller than 0. So let us note this down. The task of variational inference was that we said that Q star over the set vector is the arg minimum over all Q of set from a family, so for instance for the Gaussians, over the KL divergence of Q of set and the true posterior Well, then we said we can't compute this, but this is equivalent to saying that Q star of Z is the arc maximum over all Q of Z's from our family over the evidence lower bound. So once again, the evidence lower bound is bounding our evidence from below. And we know if it is equal to our evidence, then we found the true posterior. But we won't find it in general. So also let us note this down here, that this is usually not achieved in variational inference or shorthand VI, but we again want to find the best fit. And the best fit is then the minimum of the KL or the maximum of the lower bound. There is one last point, and I want to rearrange this equation that we had here for the evidence lower bound or for the ELBO. So we had that the KL is minus the ELBO plus the log marginal or the evidence, and this can be rearranged into that the ELBO of Q is the negative KL divergence plus the logarithm of the marginal or the evidence. And that's also an interesting finding that you might see in textbooks. Lastly, I want to look at some interactive plots in order to emphasize what these quantities mean. Here we have an interactive ELBO plot, and we have a true posterior, which for the sake of simplicity we can evaluate, and I painted it here in blue. And we have a surrogate posterior as a normal distribution for which we can change the mu and the sigma, so we can move it around. We have access to the KL divergence of the true posterior and the surrogate, and we have access to the evidence of the data because there are some observed variables, and here we are looking at the latent space. And I calculated this for you, and now we can play around with it a little bit. First of all, we see the KL is a positive quantity, and this is this one here. And we put a negative sign in front of it, as in the rearrangement we just did a couple of seconds before. Then we have the evidence, and we know the evidence is a negative quantity because it's the log probability of something. And by this, we also know that the ELBO is a negative quantity. And we see the ELBO is negative KL plus evidence. So in this case, we have a KL of 1.01 and the evidence of minus 0.03. So we have an ELBO of minus 1.04. And our task is now to minimize the ELBO, and we will see that this is equivalent to maximizing the KL. And for instance, we see, well, the peak of the true posterior is here. So maybe let's move our mu around and get it to this position approximately. And we see in our moving around, the evidence did not change, right? So it's still 0.03 because the data did not change. We just changed the surrogate posterior. But what happened is we reduced the KL because it is now closer to our true posterior, and we increased the ELBO because we are also closer to our true posterior. Then of course we see, well, probably with this standard deviation we are not getting far, so let's increase it by a little bit. This also puts our peak down, and then we see again, oh yeah, we reduce our KL even further, and the ELBO is increased again, so maybe we can go further, and let's see, maybe let's try to play around. It's probably not too necessary to find the actual optimum here, but we see we decrease the KL by 1 order of magnitude here, and also our ELBO is really close. And recall that the ELBO is the evidence if the KL is 0. Of course, here we see that our true posterior has more features than our surrogate, so we won't be able to ever get the KL of 0, but that's still quite a good result, isn't it? And we also see if we increase the sigma then even further, we can go down again, we can down again, and then there will be the point of inflection where we will be going back up again, because then we are getting further apart from our posterior again. Okay, I hope this introduction made sense. If there are any questions left, please write a comment. I would be happy to answer them. And I hope you got the main message across that we are doing variational inference. So we want to do inference. So we want to say something on our latent variables, and we do it variationally, which means we do it over potential distributions over functions, and that the ELBO is a way to express or to find an equal optimization problem to minimizing the KL. So maximizing the ELBO equals to minimizing the KL. Then thanks for watching this video. If you enjoyed it, then please consider liking and subscribing. I would really appreciate this. Here you will now see similar videos, and I hope to see you next time.